Hello everyone. I am sorry for the delay in uploading this video. But yeah, persistence is the last section that we are going to be touching on for the course. So I thank you for your patience. I have reduced the scope of this section and kept it quite tight to what I'm expecting from you. So yeah, let's just get straight into it. So persistence refers to the characteristic of a state outliving the process that created it. So this is achieved in practice by storing data, computed storage, using our hard drives. When we turn the computer off and we turn it back on, the data is still there, thankfully. So we're going to be looking today at how this is achieved. And specifically, we're going to be looking at file systems. So if you think back a little bit to our abstraction hierarchy, we abstracted memory, we abstracted the CPU. So this is a similar process, right? We're abstracting away the complexities of specific devices, such as our different hardware disks. You got your HDDs, you even got your SSDs these days. And at a fundamental level, as an application developer, we don't want to have to deal with that complex space. So we utilize abstraction. So here in this diagram, you can see we have an application, and then there is that user kernel boundary, as we've seen before. And as you will be well aware, how we interact with files is based on an API. And you've been using this behind the scenes, or not necessarily behind the scenes, but you've been using this unaware for many years now. And this API brings with it functions such as open, read, write, and close. So whether you're using Java, C++, Python, you were calling these types of functions, and they were what would allow you to actually refer to data from the disk. And this API works exclusively with the file system, which abstracts away the other layers, such as the general block layer and device drivers, which then communicate with the actual physical hardware. Cool. So we are going to be looking primarily into file systems and their functioning. The two key aspects to file systems are what we call files and directories, both of which you should be very familiar with at the moment. Okay, so we're going to develop these abstractions out and implement our own very simple file system using both of them. Okay, so the first one of these is a file. And a file is simply a linear array of bytes, each of which you can read and write to. So each elements in this array you can read and write to. And each file has with it an associated low-level name. Usually this is a number, and we call this number an inode number. And this is mainly for historical reasons. But these historical things tend to continue on throughout history. And in most systems, the OS does not know much more about the structure of the file. It doesn't really know whether it's a picture or text file or something like that. Rather, the responsibility of the file system is to simply store such data persistently on disk. And make sure that when you request the data again, that you get what you put in that same place. The next aspect, of course, is directories. So the second abstraction that we're going to be looking into is a directory. And that is similar to a file, as it also has this low-level name, this inode number, but its contents are quite specific. And specifically, it contains a list of pairs, where each of these pairs contains both a user-readable name and a low-level name. The user-readable name is like the directory name that you give like when you're making folders and stuff like that, this is the name that you give. And the low-level name is like the inode number that we've been referring to, this low-level reference. So in this case, like on the slides here, we want to maybe create a directory called foo, and it is associated with this low-level name 10. So it's basically this mapping between user-readable names and low-level names. So with that idea, we can build out something like that. So each entry in a directory refers to either the files or other directories. So contained within a directory, we will have those pairs, those lists of the user-readable and low-level names. And this allows us to place directories within other directories, which is, of course, makes sense because this is what we've been using for years. Like you obviously have files and folders in multiple subsets and multiple levels of subdirectories. So you can build out this like arbitrary directory tree under which all files and directories can be stored. And it's important to note here that at the same level, you need uniqueness in terms of the user-readable name. So you can't have two folders in the same directory called foo, but at other levels in the tree, you can have the same name. So here you can see we have two folders called foo, but they're not at the same. They're not within the same like level. They don't have the same parent. And again, that makes sense. Like when you've been all this functionality should make sense because this is how you've been using computers for years now. Okay, so with those two things in mind, files and directories, we want to build upon our own very simple file system. And this is gonna be known as the very simple file system, VSFS. So if you ever see that term, this is what we're talking about. And this file system is a simplified version of the typical Unix file system, so our typical Linux file system, and therefore it will serve as a good introduction to our basic data structures as well as the various access methods, how we interact with the file system. And these things are what you will find in many modern file systems today. So it's in no ways, inappropriate. Now, a file system is purely software, so unlike our development of like CPU and memory virtualization, where we utilized, like a TLB, which is like a hardware buffer, or that mode bit, so that we could do the dual processing, like user and kernel mode processing. We will not be adding any additional hardware features to make some aspects of the file system work better. So this is purely a logical, software-based implementation. Cool. So because of the great flexibility we have in building a file system, many different ones have been built over the years, and we'll be, like I say, going to this basic one, but I'll show you some variations to the same structure as we move along. Okay, so the first key aspect, as you can see, it's been staring at you the whole time, is data structures, the data structures of a file system. So in other words, like what types of on-disk structures are utilized by the file system to organize its data and metadata. So the first file system we will be designing employs simple structures like arrays of blocks or other objects, whereas more sophisticated ones will use tree-based structures. But like I said, we're going to start from the very basics and just build up with, arrays. The second aspect that we need to implement is the accessing methods. So how do we map those function calls, such as open, read, write, etc., onto its data structures? So how can we use those functions to manipulate our file system? The idea here being like which structures are read during the execution of particular system calls, which data structures are written to, and how can we efficiently perform these steps. Cool. With those two things in mind, let's develop the overall organization of our file system data structure. So a hard drive is a disk that contains information, and we want to represent that in some way, obviously. And for the simple case, we're just going to think of arrays. Arrays are, a contiguous region of memory that is divided into blocks. So we're going to take our concept of our hard drive and we're going to divide it into different blocks. And the way we do this division is going to be super simple. It can be, in more complicated versions, you can have different varying block sizes, but in our case, we're just going to think of a single block size. And in particular, it's going to be a block size of 4 kilobytes. So thus, our view of the disk partition where we're building our file system is simply a series of blocks, each of size 4 kilobytes. Okay, so here we have 64 blocks of 4 kilobytes each. And the blocks are addressed from like value 0 to n-1. Okay, and here again, we're going to assume we just have a really small disk with just these 64 blocks. Okay, so now we have blocks where we can put information in, but how are we going to do that specifically? How are we going to arrange that? And for some reason, my slide is not changing. Intuitively, the thing that we need to store the most is user data, right? So we allocate a region within these blocks to form the data region. And this is where the information stored within files will actually reside, okay? So we dictate the specific number of blocks to be allocated to the data region. In this case, it's 56, okay? And this is just chosen arbitrarily, and it ranges from, it's usually at the end of your file system. And here you can see it's ranging from 8 till 63, all right? Additionally, file systems have to track which data block comprises a file, so which of these data blocks make up a file. And it also needs to keep track of like the size of the file, its owner, and this is stored in an object called an inode. So we've touched on inodes already, okay? And that inode basically is telling us information about the file. Now, to accommodate inodes, we'll need to reserve some space on the disk for them as well. All right, data, exists somewhere physically. Well, the metadata of that data has to exist as well somewhere, right? So we call this portion of the disk the inode table. Okay, so you can see here we've now allocated the inode table, and this simply holds an array of on-disk inodes. So the inodes correspond to files and directories, and the inode table corresponds to all the inodes corresponding to all those files and directories. So our on-disk image now looks like what you can see in this picture here. We have our inodes, we have our data region, and we can see that we use 5 of our 64 blocks for the inodes, and that's donated by the I in the diagram here. Now you should note that the inodes are typically not very big, right? For example, they could be 128 or 256 bytes. In this example, we assume 256 bytes per inode, and therefore with a 4 kilobyte block, you can do the division there. 4 kilobytes divided by 256, we can see that each block can hold 16 inodes, and therefore 16 times the number of blocks that we have, our file system can technically hold a total of 80 inodes. Okay, this is the maximum number of files that we can store at a given time. And this limitation is purely because we've built on like our tiny 64 block partition, right? However, do note that most file systems are built on larger disks, and we could simply allocate a larger region here. Why do we only allocate 5 blocks to the inode? That was arbitrary in this case. We could have allocated 16 blocks, so to speak, and we would instantly be able to store a greater number of files. Okay, so be aware of that. Now, one component that is still needed, and I kind of alluded to it in the previous slide or figure there, that you kind of would have seen it already, is that we need some way to track whether the inodes or the data blocks are actually free or allocated, right? We want to know if the information, when we delete or create new files, we need to say if this region is in use or not. So for our allocation structures, therefore, we require an element that can keep track of this. So there are many different allocation tracking methods. One of course is something that you're quite familiar with, is like a free list, right? You could utilize a free list to tell us which of the data regions are empty, and a separate free list to tell us which of the inode regions are empty. So we're going to instead choose a more simple approach, but quite a popular one, and that is to utilize a bitmap. So not bipmap, but bitmap. And we'll have a bitmap for the data region and a bitmap for the inode table. And you can see that here, this lowercase I and lowercase d. And a bitmap is a simple structure where each bit is used to indicate whether the corresponding object is free or in use, like 0 or 1. So here we have essentially like an array of objects, and you would have a corresponding bitmap of the same length. And if this element here was free, well, then the first element in our data bitmap would be 0, right? Because it corresponds to whether or not this is in use or not. So these elements, these two arrays here, or rather strings, if you want to think of it like that, let us know or indicate to us which of these regions are in use or not in use. The last thing is this final or first block here, and that is usually reserved for the superblock. And the superblock contains information about this particular file system. So includes how many inodes there are, the number of data blocks in the file system, so 80 and 56 respectively in this case, where the inode table begins. So here it begins at block 3. Okay, and it will also include a magic number of some kind to identify the file system. So therefore, when mounting a file system, the operating system will read the superblock first to initialize some various parameters, and then attach the volume to the file system tree. And then when files within the volume are accessed, the system will thus know exactly where to look for the needed on-disk structures. So basically, the OS will use the information stored in the superblock here when mounting the hard drive to be able to read everything inside of it. As you can probably tell, one of the most important parts of these on-disk structures is the inode, right? Because it tells us all about files. So virtually all file systems have a structure similar to this, and the name inode is short for index node or index number. And each inode is implicitly referred to by a number which we can also call the I number. So there's also just various jargon around this, but inode is like a number which we're going to be thinking of. And previously we called it like the low-level name of a file, but yeah. In our very simple file system, given an I number, you should directly be able to calculate where that, where on the disk the corresponding inode is located. So I'm gonna just show you this worked example here. So for example, we have this inode table. Again, we have a super block, our inode bitmaps, our data bitmaps, and then our inode table, which is those 5 blocks. Okay, and you can see this inode table starts at like 12 KB and ends at 32 KB. Okay, and specifically in this example, we're trying to look for the location of inode number 32. So this process that we're going to be taking is somewhat similar to how virtual addresses are translated into like physical addresses in a way. The idea here is that we know that our inodes are like sequentially laid out, as you can see in this like grid-like fashion. Okay. And we know the inode number that we're looking for, which is number 32. So this will be like 32 like units away from the beginning. So in order to calculate where on the disk the corresponding inode is located, we first need to calculate an offset and then add that offset to the start location of the inode table. So to calculate the offset, we take the inode number, so in this case 32, and we multiply it by the size of the inode. So if you remember back to the previous couple slides, we said 256. So 32 by 256 gives you 8192, okay? And that tells us like within the inode table, how much must I shift from the beginning to get to the inode I want, okay? Then all we simply need to do is take the start address of the inode table, because this could technically be anywhere in our like file system. So we take the start of the inode address, the start of the inode table, and we add it to the offsets. So we get 12 plus 8, and we get 20. And you can see even in this diagram, like if you knew explicitly this, like you would have seen that, okay, we should expect to get the value 20 because that will be over here. Cool. Yeah. Now, as previously mentioned, the inode, stores a lot of the good information that we need. So primarily it tells us the file type. So this is a little bit like, not the best terminology, but it's how it works. So file type can either be one of two states, essentially, either a regular file or a directory. So a regular file is like, .txt, .png, actual files. And then a directory is, a directory. That should be familiar with you guys. And then it tells you the size. So the number of blocks allocated to it. Okay, so how many blocks are used to store the information for either the regular file or the directory. Its protection information, so this is like, read, write, access privileges, all that type of stuff. The time information, so when something's been accessed, when it was last changed, this type of stuff. And you can actually see this information pretty easily. Whenever you have like a file and you go like right-click properties, all those properties are stored in the inode. So that's what it's referring to there. Now you might be asking, like, in our file system, we can't actually store that many files. So how does it, grow bigger and bigger and bigger? We've got like petabyte drives that you can actually get, and this type of thing. Well, how it works is that you utilize what is called this multi-level index idea. And essentially what you have is, instead of a inode, pointing directly to a data block, these are what we call our direct pointers. You can also have a indirect pointer. And the idea behind an indirect pointer is that it will point to a block which contains pointers which will then directly point to actual data regions, right? So the idea here is like, say we have 12 direct pointers, okay? So we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 direct pointers that are pointing to blocks of data. We can also have an indirect pointer which gets allocated once a file grows large enough, right? If we exceed the amount of data we can store using these 12 direct pointers, we have a slot for an indirect pointer. And then this indirect pointer can point to a set of blocks of its own right. So if I go to the next slide here, we can see a little bit more how this works. So we have a block size, right? In the case that we've been working with, it's been like 4 kilobytes, okay? And we have an address size. Okay, let's just, for example's sake, say the addresses are pretty small, like all, 4 bytes each. Then we can say then that each block in our file system can potentially hold 1,024 addresses, okay? And each of these addresses can then be their own, subsequent direct pointer. So now we can have, with a single indirect pointer pointing to a block of 1,024 direct pointers, we can obviously point to a lot more data blocks, right? So what you can see here is that we can have 12, right, plus 1,024 now in this case, all right? 1,024 blocks rather. So now we have 1,036 blocks where each block in itself can be, is 4 kilobytes. So therefore you can point to a much larger file than we could possibly do before. Now this idea obviously can be expanded on tremendously, right? What's to say that we only have one indirect block? We can have multiple indirect blocks. We can also have double indirect pointers, such that we have an indirect pointer pointing to a block of indirect pointers, which then in turn points to direct pointers, which finally points to our actual data. And then you can have triple indirect pointers, and this can get quite out of hand very quickly. And by doing this process, you can actually have files that grow to over 4 gigabytes in size, which is something quite common today. So what you tend to see is something that looks a little bit like this flow diagram here. Okay, so with, say, a double indirect pointer, so it points to a block that contains indirect blocks, we can allow a file to grow with an additional 1,024 pointers. But if you expand this over and over and over again, we have what you can see here. So we have like that original idea of 12 direct pointers, so 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. We have a indirect pointer, which points to a block, all right, which in turn will point to the data, all right. So that's the 1,024 over there. And now if we had that double indirect pointer, would have that points to a block, which in turn each points to a 1,024 more blocks, which then it points to 1,024 more blocks in its own right. So we have this idea of 1,024 squared here now. And then each of these, this is essentially the number of blocks you're pointing to. Each of these blocks is 4 kilobytes each in this case, and then you can see how this can grow, exponentially like that. Obviously, the drawbacks of this approach is this tree-like structure is a little bit more complex to traverse, but it allows for much greater file sizes. So that was files. Let's touch a little bit more deeply on directories. As I mentioned, a directory is just a list of the entry name and inode number pairs. Okay, so if we look at this example, assume we have a directory whose inode number is 5, okay, and it has 3 files in it, foobar and foobar, and those have inode numbers 12, 13, and 24 respectively. The like on disk structure would look something what you see here, right? In this example, an entry inode, it has an inode number, a record length. Okay, this is like the total bytes to represent the name, and then string length is the actual length of the name, and then the name of the entry. So you can actually see here in all directories we also have this dot and dot dot file. And this is what allows us to use like ls dot dots and ls dots and those types of functionalities inside terminal, because they have like their own like inode representation inside the directory. They themselves are referenced there. So dot represents the current directory, and then dot dot represents the parent directory. So you might be wondering where exactly directories are stored. Now, often file systems treat directories as a special type of file. Thus, a directory has an inode somewhere in the inode table, with the type field of the inode marked as directory, like I was touching on before, and that is now instead of like quote-unquote regular file. The directory has data blocks pointed to by the inode, as well as perhaps like indirect blocks, and these data blocks live in the data block region of our file system. I know this may be all a little bit complicated, but we'll be going through a worked example at the end of this presentation, and that will clear everything up real quick. So now that we have an idea of how files and directories are stored, we should be able to flow the operation of like reading or writing to a file. So whenever you've used this, you've used open before, I'm sure, okay, and you'll give it some sort of path name, and then that would like open the file, or it will return a file descriptor, which would allow you to do stuff like read line and write line and stuff like that. So the general process works by first we traverse the path name, and then as a result we locate the desired inode of the file that we're trying to open. Okay, in this case bar. So we'll traverse from root to foo and from foo to bar. So we begin at the root of the file system, indicated by like the forward slash. And traditionally most Unix file systems have a root inode number or 2, but it doesn't have to be. So file system then reads in the block that contains the inode number 2, which corresponds to the root. Okay, it looks inside it to find the pointer to the data blocks. So we look at the data block associated with root, so the data block of root. And then by reading one or more directory data blocks, it will find the foo directory, right? It's not guaranteed that foo is the only directory inside root. Therefore, we might have to read one or more. So it will find the foo directory and then traverse recursively the path name until the desired inode bar. So it will kind of repeat this process. It will get the foo directory, which is the foo inode. It will go to the foo data block, and then inside the foo data block it will go again and again. Finally, it will check permissions and then allocate a file descriptor for this process. Then it will then return that file descriptor, as of course you're aware. Now, when we're trying to read, from a file, we need to read in the first block of the file, consulting the inode to find the location of such block. So when we're reading from that file, we'll look at that inode. We will update the inode with the last time it's accessed, so like the current time. And then we'll update the file table for the file descriptor by the offset. So when you read like a next line, it will update such that next time you read, you'll be reading from the next offset. And then when the file when the file is closed, the file descriptor should be deallocated, but you don't have to really worry about this one. Cool. So we're going to work through a timeline here. Okay, so time is increasing downwards, and you can see the different system calls over here on the left, or the API calls rather. And then on the top, our x-axis, we are listing the different objects that we are reading and writing to. So we want to assume firstly that we just want to open a file called bar. Okay, we want to read it and then close it. And for the simple example, let's assume that the file is just 12 kilobytes in size, so therefore it's just 3 blocks. Okay. So when we issue the open call, the file system first needs to find the inode for the file bar in order to obtain some basic information about the file, such as permissions information, the file size, and get that file descriptor. So to do so, the file system must be able to find the inode, but all it has at the moment is just the path name, right? The only thing you feed into this open function is the path name. So therefore, the file system must traverse the path name in order to locate the desired inode. All traversals need to begin at the root of the file system, which is in the root directory. And again, it's indicated by the /. So the first thing that the file system needs to do is read from disk the inode of the root directory. The question is where is this inode though? We know that to find an inode, we must know its inumber. And usually we find the inumber of a file or directory in its parent directory, right? The root, though, has no parent. By definition, it's the root. Thus, the root inode needs to be well known. Okay, so the file system needs to know where this root inode is, and that is initialized when the file system is mounted. So this will be governed by the superblock and initialized by the operating system. Now, in most Unix file systems, the root inode is 2, but again, like I said initially, this can be arbitrary. In questions, in tests and stuff like that, you will be told where the root inode is. Okay, so to begin the process, the file system reads, reads in the block that contains inode number 2. So here you can see that read. Okay, once the inode is read in, the file system can then look inside it to find its pointers. So it reads this and then looks inside such that it can locate the data for the root's data, right? So then it reads the root's data. Inside the root's data, it will actually let us know that, this directory contains other directories and stuff. So, some of which is this foo directory. So it will point us to the foo inode. Okay. We then read the foo inode, which in turn points us to foo data. And then foo data will, point us to the foo inode for the bar file, right? Because again, this foo is a directory. Directories contain the pointers as well as the names of the files and directories that they contain. So it will tell us that it contains bar. Bar is what we're looking for, so therefore we read the inode of bar, and that's what we want, right? We want to find the inode of bar. That is what open is doing. Cool. So now we want to read data from that file, correct? So therefore we run the read commands, like read line or whatever, like while not end of file read line. That's a classic one. This is what we would do. We read. So we need to read the inode, which tells us where to find the particular data. Okay, and we're reading in data chunks one by one, all right, blocks by block in this case, all right, because we said that we want to read a file that has 12 kilobytes of data, which is 3 blocks. So we read the first block here, and then we write information. Okay. The writing that we're doing here is to indicate or to update the last time we've read, like we're updating the metadata. We're not actually updating the data, and hence we write to the inode and we're not writing to the data. We then issue another read, we do the same process, we issue another read, we do the same process on the data blocks 0, 1, and 2 in this case. Cool. I hope that makes sense, because that is a pretty straightforward example of accessing and then reading from a file. Now, writing to the disk is a little bit different, okay, because we need to update the data block as well as the data bitmap, okay. So when we issue write to update the file with new contents, we may allocate a new block, unless we're overwriting something, and therefore that's why we need to update these things. So this process actually generates 5 input-output like requests. One to read the data bitmap to see if this is free or used. One to write to the data bitmap to reflect the new states, because we want to write something to the disk, so we need to say that it's not free anymore, so it's used. 2 more read and then write to the inode to update those, okay, and then 1 write to the actual block itself, okay. So to create a file, it also allocates space for a directory, and this causes a lot of high input-output traffic. So on this slide here, we have that same flow diagram timeline idea for writing to the disk. Okay, so create is what is used to create files. In this case, we want to create a file called bar inside the directory foo inside the root directory. Okay, so once again, we have quite a few read writes to process. Okay, firstly, we read the root inode, which will then read the root data, which will then read the foo inode, which will then read the foo data. And this process is simply to traverse our directory tree in order to get to the location where we want to write the file. Now in this case, we need to read the inode bitmap to see which inodes are free, and then we need to write to it indicating that we've created a file and we've written that information to a new, we've indicated that a new part in that bitmap is now used. Okay, then we need to actually write information to the foo directory indicating that a file is now going to be contained within it, okay, because we need to update that information. And then we need to read and write bar, okay, such that we're actually writing the file, all right. And then we also need to rewrite the foo inode to indicate that maybe the foo directory has changed, okay. So there are those 5 different processes that really need to happen. And then, so this is on just creating a file. Now the writing process, okay. So the idea that I want you to understand here, that the read and writes to the specific parts here don't need to necessarily happen at the exact same time or in these sequences. They can happen asynchronously. So firstly, we read, we write to the bar inode because we actually want to write data to it. So we want to update that inode to reflect that it needs to point to maybe other blocks. And then we need to check in the bitmap to indicate that we are updating actual blocks of our file system, right? Just like we did with the inode. And likewise, this process happens 3 times because we want to do 3 writes and to 3 different data blocks. So this write here, if we're just looking at the second row, will be doing the write process that updates our bar inode, which is our bar inode file, to say that, oh, this file now contains data in this block here, in this bar block here. And likewise, this write is corresponding to this block here, and this write is corresponding to this block over here. Now you can see that this process of reading and writing files is quite expensive and occurs many input-output processes. And that was for quite a simple path name, right? There were only a few directories that we needed to traverse. So for long path names, which many subdirectories, this process becomes very, very taxing. So in order to reduce I/O traffic, the file system will aggressively make use of the DRAM to cache like popular blocks and these popular like inodes. Okay, just like we cached popular memory address translations in our TLB, we want to cache these lookups such that we don't have to do this traversal so many times. And lastly, it also uses what we call buffering. Okay, so file systems also use write and read in write buffering rather, such that we buffer writes together, or we delay writes such that we can do them in one big batch. And by batching them together, we can reduce the number of I/O requests by avoiding unnecessary additional writes. So in the previous example where we had write, you could see that we were reading and writing and updating the bitmaps and the inodes and the actual data multiple times. Well, why not just update the inodes all at once, right? And update the bitmaps all at once. These are things that we can do and are a lot more efficient. Okay, so here is the worked example I promised to help, conceptualize everything and make things a little bit easier. And it is also, so maybe hint here, it is also the similar format to like the type of question you will get in the exam, okay? So this builds up on everything that we've been touching on today, and I will be explaining some of the questions that I would ask given this structure. So it may look a little bit confusing, but it's exactly the same. All right. So we define our file system to be made up of, in this case, 20 blocks. So block 0 all the way to block 19 here. Okay. I stipulate which block corresponds to the super block. I stipulate which inode is the root inode. So in this case, inode 1 is the root inode, and I'll explain why it's 1 in a second. And then the rows of these blocks, tell us information that is stored there. So in the case that the particular block is an inode, okay, the first row is indicating the type, so whether it's a directory or that regular file. The second row indicates the size. The third row is a pointer, like the pointer to the particular data block. Okay, and then pointer 2 is the pointer to the second data block. Okay, now if it's a directory, the first row is the human readable name of the first file in that directory, and the second row is the corresponding inode. The third is the human readable name of the second file and the corresponding inode for that second file. So here you can see in this very, very simple file system, our inode can only ever point to 2 blocks, right? 2 blocks here. That's the most it can point to. So that should influence some of the questions that you will see, so that's worth understanding. Okay, so one question, last thing, sorry. I will also indicate which regions correspond to the inode table and like which regions correspond to the data blocks. So in this case, the inodes are from 1 to 9, and our data blocks are like 10 to 19. Okay, and it's important to note that inodes are numbered like 0, 0 to like the n-1 idea. Cool. So if I asked you what is the inode number of the root inode, well, it's 1. Okay, so that should be pretty straightforward. Okay, then the next type of question I can ask you was, well, like, what is what are the files and directories immediately in the root inode? Okay, so how would you read that? Right? Well, we know this is an inode, and we know when we're reading, we always start at the root. But I've told you I want you to start at the root, so that's doubly true. All right, so then just let's look at this. Well, this is an inode, so what is it telling us? Well, we know that it's a directory or file. Okay. In this case, 1 indicates directory and 0 indicates file. Again, that will be stipulated. So we know, okay, the root, well, it's a directory, right? So we knew that already, and it's indicated here as well. All right, it's of size 1. Okay, so that means it has 1 pointer. So we don't even have to look at this. All right, and it's pointing to block 18, not inode 18, block 18. All right, so it's pointing over here. Okay. So it points to some data block, right? You remember when we were doing the traversal? You know, when we're accessing, we go in inodes to data block back to inode, inode back to data block. That's how it kind of works. This is that first like jump, right? 18 indicates this data block. Cool. So we know that we've come here, and we know that we've been here. Okay. So we know, if I'm just going to draw the hierarchy out a bit, we know we have our like root. Okay, just going to indicate it like that, and it branches into something. What is that something? Well, let's look. So we know that it's pointing to a directory from here, okay, and inside that, well, sorry, we know that it is a directory, okay, so that's that, and we know, we can see here, okay, so the name of the first file inside our directory is bar. Okay, so one thing in this directory is bar, so we know that, and then the other thing is I, so we know that it's I here. We don't know if these are files or directories themselves yet, but we get in there. Okay, so let's start at the first one. So bar, okay, points to inode 0. Okay, so 0 is this one here, right? Inode 0, as you can see here. Okay, so what is bar? Well, let's check. Oh, it says 1, so we know bar is a directory itself, right? So we're just going to put a little liney there. Okay, and then the other thing is that I was pointing to inode 2. Okay, so this points to this inode here, right? This one here. And what does that say about I? It says that inode I is also a directory because it's a 1 here, right? These are both 1s, so they're both directories. Okay. And we know that this was a 1, so it only has 1 pointer, so I didn't have to deal with this. So essentially, the things in our root are the folder bar and the folder I, right? Like that's what's immediately in the root. Okay, that's all we know so far about the root. So that could be one question, right? It's like, what is immediately inside our root directory? 2 folders, bar and I. But then I could say, like, what are all the folders and files found within our file system? Okay, so that's a slightly different question, right? And what you would need to do is then continue traversing along. So I'm going to do the left-hand side of this tree. Okay. So where were we? We were over here, right? Bar was inode 1. Okay, inode 1 is a directory, size 1, so I can ignore whatever's here. All right. Points to data block 10. Okay, so that's nice. It points here. Okay. So I know inside bar now is something about goo and something about CS, right? So goo and CS. Okay, so let's continue the chain. Okay, goo has an inode at 3. All right, so that's, if I snake it along here, that's that one. All right. And CS has an inode at 4, which is this one here. Okay. So what is 4? 4 is 0, so it's actually a file. Pretty cool. So we know that goo contains a file, right? And specifically, goo is a file. Sorry, it doesn't contain a file. It is a file, right? So what does goo contain? So I'm just going to draw like a little bracket here. Maybe not. I'll just say goo over here is equal to, because it will have some information in it, right? Okay, what is CS? CS is also a file. Okay, so CS is also a file. Okay, what do those files contain though? That's the interesting thing to ask yourself. So 4, it's a file of corresponding with 2 data blocks. Okay, 11. Maybe I'll do this in a different color. Let's go purple. Okay, so 11. No. What? Give me one more color. That's all I'm asking. 11 is this data block here, but it's 2, right? So I can't ignore this. And 14, this over here. So 11 has the data 3, 4, 5, 6. And this is for the goo file. So we have 3, 4, 5, 6. And 14, A, 10, B, 12. So what, if I had to ask, like, what is in the file goo, you will say this like string of data, 3, 4, 5, 6, A, 10, B, 12. All right. And now what is in the file CS? Well, it says 1 here, so it's of size 1. So I ignore this, all right, and I go to block 13. And that has 7, 8, 9, 10. Okay, and because these are files, right, we're not pointing again, they're not directories, right? They don't point to other inodes. We're just done. Okay, and then subsequently, if I wanted to see like what's completely contained within this file system, I'll do the same process for I. All right. So these are the types of questions I will be asking you as a student. You need to be able to traverse a file system in this manner. You need to tell me maybe what files, what data files contain, what folders and files and names and stuff are in the file system. Perhaps I'll ask you some questions like what can be accessed, what can't be accessed, these types of things. But yeah, in general, that is it. So I hope this all makes sense, but if you do have questions in the week, feel free to email me. Thank you.